right? Can people hear me? Right. Right, hopefully it's set up right. You should be seeing like a Spider-Man PS4 logo thing right now. Right, it's just there for background. We'll probably start in like 5 minutes. We'll start off with vector spaces because 2501's got to be here as well. So I'll go over group theory at the very end. I suppose it'll take like 30 minutes-ish, but I'll reiterate that when we start in like 5 minutes. Right, turn the mic again. Right. Wait, does that work? I'll read back to the screen. Let's see. It should be fine. Yeah, I'll start in like 2 minutes time. If you guys have anything in particular you want me to go through, alright, feel free to let me know, like whenever. Let's see, I'm still chatting. I'm going to change the color quickly. That's not good. Right, might as well start, I guess. Yeah, I think, yeah, doesn't seem like anyone else is coming in. Alright, so I'll just start. So the way it's currently set out is that group theory is first, but then since this is 2501, 2601, I'll just kind of leave that to the very end. Okay, for some reason it's popping up. Right, so I'll just move down to baskets. Right, group theory will be at the very end, and we'll just go through vector spaces first. Right, should be fine. And vector spaces. Okay, for some reason it's not appearing. Right, so the idea of vector spaces we did in first year. Right, so I kind of just said the formal definition is just the 10 axioms you remember, but not really. I'm not going to really go through that because, well, you kind of need to know it, but again, it's not that important. It's kind of like like this, like if you don't know what I'm talking about here, it's the associativity, and stuff like that, right? It's just things you kind of know, but you might not know the exact names of, right? Alright, so the more important thing is subspace theorem, right? Again, from first year. The idea is basically you have a subset, but you want to prove that it contains properties of a vector space, right? And it's a lot easier to prove something is a subspace than directly prove it's a vector space. Because vector spaces have like 10 different axioms you have to prove, right? The 10 axioms. Whereas here, you just really need to prove this one statement. Well, assuming it's not empty, right? From first year. And then as you can see, these three are kind of joined in this one kind of proof, I guess. Right? You just set lambda and y to separate values to prove certain things. Right, that's fine. So let's go through an actual example. Right, here's an example. The idea is we have a 2 by 2 matrix. So we consider the matrix is by 2 by 2, real. Right, because these are all real. 2 by 2 real matrices. And we want to prove that this particular set is actually a subspace. Right, so the way you'll go about it is basically you just use the theorem above, read it. So you need to consider any arbitrary x, y, or any arbitrary, vectors, so in this case matrices, and one scalar. Right, so that's what we're going to do. Firstly, you consider two matrices in the set. That's going to be W1, W1, and a scalar in the reals, because again, this is over the reals. Right, so you just kind of combine them. And then now you need to prove that this thing is in W1, right? And then all you need to do is look at W1, just stare at it for a little bit, and go like, okay, these are the properties for it to be in W1, right? It has to have this kind of pattern, right? So 3 times the first 1 element. This element here is the first one minus the second one, stuff like that, right? We just do this. And here, since it's matrices, matrix addition and multiplication is really straightforward. So just straight up kind of do that. Right, so all I did here was combine, bam, bam, this thing, and this thing, you get this thing. Right, and then you do a similar thing over here, and you get this, and you get the idea, right? Just do one by one, and you will see all these things. Now, I would group, so the more important thing here is I group this one with this lambda and this free y1, and you'll see that that corresponds to this element here. And I made sure to factorize out the 3 to emphasize the fact that if you look at this over here, you see this is 3 times the first element, right? So this is our first element in our new context, and that's the same thing as this. But you also notice very simply that this is 3, 3. And you can notice the same thing with this thing as well, this thing, right? I should probably get rid of the red because this goes to minus, right? You can see there's a minus there, and very clearly here as well, right? So you basically proved in your context, right? In your new context, x1 plus lambda y1 is your new x1, and my x2 plus lambda y2 is your new x2, right? So you just kind of state that, right? But you need to be a little more careful when you state these things, because you need to make sure that x1 and x2 are also real, right? That's the condition you need. So you need to show that this and this thing are both real, right? But that's easy because you're just adding and multiplying reals, so it must be real anyway, right? But if you were to be careful in the proof, you need to kind of state that kind of thing, right? That kind of thing will pop up later on. So yeah, and we prove that lambda x plus lambda y is in W1. And so by the subspace theorem, you show that W1 is a subspace of the 2 by 2 real matrices. Right, straightforward. So now we just go through span. The concept of span is, well, from first year again, it's literally just you consider a set of vectors, those should be bolded, and you just consider all possible linear combinations of these vectors. Right, so lambda 1, lambda 2, lambda n, these are some arbitrary values. And we call it a spanning set if these vectors, well, like you can represent any vector in V by a linear combination of these vectors. Right, so it spans the whole set. Right, that's fine, reverse here. Again, another concept of reverse here. The idea here is that linear independence really just means that every vector, every vector is basically, you can't represent it with any of the other vectors present within the sum. Right, so that's why the coefficients must be 0. Must be 0. Right, and then in the case where they're linear dependent, then some of the coefficients can be non-zero for it to go to mapping to the 0 vector. Right, that's fine. Right, and we'll just go through an actual question of how you would show linear dependence or independence. Right, independence is the easy one to show. Dependence is more case specific. Like you have to know more about the set, but I'll show you what that means later. So we go for this. Right, we want to show these 3 vectors are linear dependent or independent. Right, so for now we'll just consider the matrix. Right, because this is from 30 again. I'll just do 1, 2, 3. Just list out the vectors as columns of your row reduction and just kind of reduce everything. Right, all I did here was I brought this thing down here. So R1 minus half R2, and you'll get this and row reduce. Now, and since it's already in the row reduced echelon form, right? You can notice that, as you can see here, there are 3 leading columns. And so that means the set of solutions to this, the solution to these set of equations are unique. Right? Since the solution must be unique, that means the only solution to this must be the 0 vector. Only solution. Right? And since 0 vector is the only solution, then that means it must be linear independent. Right? Because that's what linear independence means. The only solution is the trivial solution. Right? That's how you would show linear independence. Now for dependence, you need to be more careful. You need to understand what the relationship between the vectors are. Right? So you need to have some foresight beforehand. And this is an example. So consider this set here. Right? Cos, sine, and sine x plus pi 4. Is this set linear independent? Well, I can't really say it, but it's not. The reason being is because you can legit just observe this property, where you can just kind of do the sine expansion. So if you guys don't recall, it's this one. Sine x plus alpha, sine x, cos alpha, plus sine alpha, cos x. Right? And alpha is pi 4 in our context. So that's what this and this are. And you can clearly see if you bring everything to one side, you will have non-zero coefficients that map to 0. So you just do just minus, plus, and this will equal to 0. Right? Non-zero coefficients that map to 0, i.e. you have non-trivial coefficients that map to the 0 function. In this case, because functions are vector space, it must be linear dependent. Right. So you need to be more careful with linear dependence because you can't just rely. You may not be able to rely on matrix reductions, especially when you're dealing with functions. You need to understand what the functions are. Right. So move on to the next concept, basis, from first year again. This really just combines the idea of a spanning set and linear independent sets. The reason being is because you basically want a set that's minimally describes the whole vector space, right? And by having them being linear independent, that means every vector is actually contributing something to your sum, right? So pulling their own weight. And spanning because you want to represent the whole set. That should be fine. And some notable properties, these are not too difficult. The main thing you you have to be careful with basis, is that it depends on the field accompanying the vector space, right? This is something new to this course, I imagine. Like in first year, you probably just kind of went with it. They don't really tell you what field is. But the idea is, like, if you consider this and this, right? The basis for the first one isn't just 1. You have to consider the imaginary numbers as well. The reason being is because you can't just multiply the 1 by a complex number to represent a complex number, right? Whereas this one, you can just straight up just use 1 as a basis, right? So your field that influences the basis you choose. That's something you have to be careful of, right? And we have something called standard bases. This is just ones that, well, they're very simple, right? They're very intuitive, and it's good to be familiar with a few of them for each vector space you're familiar with. So like Cn, for example, or polynomial nr, and this one being 1t squared all the way to t to the power n, right? And the reason why it's good to be familiar with them is because of the next thing, right? Again, first year result, dimensions. All right. The main use of dimensions, it's really just the number of elements in the basis, is the fact that it can reduce the amount of work you need to do to prove that something is a basis, right? Again, first year again. The idea is if you can prove that it has the same number of elements and it's linear independent or it's spanning, then it must be a basis, right? This isn't too hard to imagine, right? You just replace potentially, right? Because before the original case, you need to prove this, linear independence and spanning. That could be annoying, like, because like, well, okay, it's not that bad, but by noting the dimension of the set or vector space, you half your work, right? You don't need to do as much. And here's an example, really. So you consider the degree 2 polynomial space, P2, over the reals. And we want to show that this thing is a basis of this vector space. Right, so the first thing we note is, we'll just use the result we just talked about earlier. A basis for this, the standard basis for this is BP, or S, I'll just write S, 1t squared. Right, because you can always break down any single vector or polynomial into these components, and obviously they're linear independent. Right, so there must be a basis. This tells you the dimension of this thing is 3. It's 3. And you can clearly see this has 3 vectors or 3 elements in it. So you only need to show whether it's dependent or, okay, you only need to show it's linear independent or spanning. Right, you can go one or the other. In this case, I'm going to go with linear independence. Right, because spanning is a little more annoying. And in this case, there's actually a very easy way to show linear independence. It's to consider 3 distinct values and sub it in. So the number of vectors you have, the number of values you sub in. Right, so if I had a 4th one here, so say like this x power 3, I'll sub in a 4th value, right, like 3 or something. Right, but in this case, we only have 3 vectors, so just consider 3 functions. So I just sub in 3 values. Right, I sub in -1 to this, and they become out my columns. So you sub in -1, so -1. No, wait, no, they become the row. Oh, oops. Okay, each value corresponds to a row. So this is -1, this is 1, and this is 0, 1. Right, whoops, -1, 0, and 1. Right, so the first row corresponds to that value, and the first column corresponds to the first vector. Right, so this is 2 plus 3x evaluated at these 3 values. So if you look at this one, 2 plus 3 times 1 is 5, and 2 plus 3 times 0 is 2, and you can clearly see this thing is also the second column. Right, and just keep going. And here all I do is row reduce. Row reducing is fine. And eventually you'll see that it'll come down to this. You look at the first row, this thing must mean it's 0, right? This element must be 0, so alpha 2 equals 0. You go down to this one, this must be 0, right? Because of the first one. So this alpha 1 must be 0 as a consequence. And you do the same thing here. This must be 0, so this thing, everything is 0, so alpha 3 must be 0. Right? So I showed the coefficients of this sum that maps to 0 must be the 0 vector. Right? And you can clearly see the only solution is the trivial solution, hence it must be linear independent. One thing I do want to say about this technique, and then obviously by dimension theorem, we showed linear independence and same number of elements as the basis, same dimension I mean, and thus it must be a basis. The other thing I want to note of this example is that this technique of subbing in only works if you're trying to prove, only works for linear independence. You can't use it as a way to prove linear dependence, right? Because should I explain? Okay. The reason why it works for linear independence are you choose random numbers as x. In a sense, yeah, you should have some sort of intuition as to whether it's going to be linear dependent or independent, right? But you have to be careful sometimes with your choice of numbers because you don't want to end up having like two rows being the same, right? Like if two rows are the same, then obviously you're not going to get a trivial, you're not going to get an invertible matrix. And so you'll end up having a non-trivial solution, right? So yeah, you usually pick three somewhat random numbers. Right, so you go with that. And we'll move on to coordinates. Okay, again, the context of coordinates, again, is from first year. To describe it briefly, it's pretty much because when you think of the Cartesian plane, you can describe every point as a coordinate, right? So the idea is we want to extend that, but we just use basis instead, right? So we extend it to a more general basis. So if you know the basis, you can describe each vector with respect to that basis. And that's what this is. Right, just find the coefficients such that this is true. See alpha I, alpha 1, all the way to alpha n. And you will see this notation quite a bit. It just means with respect to this basis. Right. And the way you can find this, okay, how do we find it? The way you find it, the most basic way is to do the matrix approach, right? If you have like, these things, so like 1, 0, 2, negative 1, 3, stuff like this, right? So vectors that you're familiar from first year. If you're dealing with functions, so like something like x squared, x plus 1, x cubed plus or minus 7, you could potentially do this, but there are maybe different, or there may be more efficient ways, such as subbing in n different values and finding the coefficients for polynomials, right? Like we did before. Right, and the reason why you can do this is because you're assuming it's a basis, so you don't need to prove linear independence because you already know it. Right, so you go with this. We'll just go for an example here. So we're going to consider the vector space of all 2x2 symmetric matrices. Symmetric just means when you transpose it, it's the same thing. Right, you just flip it. Flip the rows and columns, same thing no matter what. You can see that here. Right. And now you want to find the coordinate vector with respect to this basis here. So they give you a basis, they give you some sort of element they want you to find with respect to, and so you just find it. Right, so you go here. Now, so again, this is just the setting for coordinate vectors, what it means. And the way you set it up is all you do is you look at each element within the matrix. So you want to make sure these two matrices, because these are 2 by 2 matrices, right? At the end of the day, they just come down to 2 by 2 matrices. You just make sure the first element of each one match up, right? So if you look at over here, you'll see 1, 2, 4, 1. Okay, let me press that. 1, 2, 4, and that corresponds to 9. Right? Do the same thing for the second one. -2, 1, -1, 5. -2, -1, -1, and 5. Right? And then you notice that this one's actually the same thing because it's symmetric, right? So don't worry about that one. And then just do the same thing for this very last one. 1, 3, -5, -4. 1, 3, -5, -4. Right. So in this case, it depends on what type of vector space you're working with. But since we're doing matrices, we just match the index values. Right, so I'll just erase all this because it's just kind of blocking the view. And here, just row reduce. Right, row reduce is something simple for this here, so I'll just kind of skip all that. Right, you can look at it later. Should be fine. And you just go, you look at this one, and you see that alpha 3 must be equal to 88 on 52. Right, and that's divisible by 4, so 22 on 13. Sub that into this one. Right, sub this in, and you'll find alpha 2 and alpha 1. Right, and hence you found your coordinate vector, right? These 3 represent your coordinate vector, and now you just need to make sure you put it in order. Alright, so alpha 1 goes first, obviously, alpha 2 goes second, alpha 3 goes third. Right, and hence the coordinate vector of A with respect to this basis is that. Shenanigans right here. Yeah. So far it's mostly revision in first year. This is kind of where the newest thing pops up, I guess. Yeah, it's probably the newest thing. Or the first time a new thing pops up, I should say. Basically, you know what subspaces are. Now we're going to introduce some of subspaces. The idea is basically, it's pretty much what the name says. You summon vectors from each subspace to build the whole set, right? It's nothing too crazy. And the reason why you kind of might want to consider this is because it actually has quite a nice, what's the word? It has a nice property that might remind you of sets in general, right? And that comes on the next slide. But we also have some extra notation, direct sum, that we call this a direct sum if the intersection of u and w is the zero vector only. Right, and the reason why it's a zero vector is because every subspace must contain a zero vector, right? It's just as a result of the properties, right? Then you have this. But the property I was mentioning earlier about some of the, what do you call it, set relationships, is this cardinality relationship thing. So what I'm talking about is, suppose you have two sets, A and B. If you do like Math2501, you'll probably have seen this thing, right? This looks very similar to it, right? So A is your U, B is your W, A, B. Now the only difference is the fact that, well, this isn't a union, it's a sum. But it looks very similar other than that, right? So if you want to remember this, you could just remember this thing. Right? And the use of this theorem is kind of like the rank nullity in a sense. Similar. You use it to prove like whether you want to find a dimension of some other thing given everything else. Right? So similar in use. Similar in use. So just go through that. Go through an actual example. Oh, are you recording this? This should be recorded. Right? The recording should be up because, yeah, it should be recorded. Right, so W. Right, we'll just go through an example. Because before I just kind of went through a mouthful. But yeah, I'll just make sure we'll go for an example so it's more understandable. Right, So we consider W, and this is a vector space over the reals, right? This is very important. You have to make sure you know what the field is. It's very important. And you notice it's just this thing. And you'll see that it's complex given the definition. And this is real, right? And we have the usual addition and scalar multiplication. And scalar field is the reals. Now, what is the dimension of W? Well, if you want a dimension of a vector space, you need to find a basis, right? So we need to construct some sort of basis for W. So if you consider some vector W in capital W, it must have the form where you have x1 plus iy1, x2 plus iy2, and x3. Oops, actually let me fix that up so it's not as ugly. Okay, it's still pretty ugly, but you get the point, right? Right. So I just made sure that it's in this form. The reason why I made sure it's in this form is because of the fact that the field is the reals, right? Since the field is the reals, your multiple, your scalar term, must be a real term, right? So you can't just leave this as Z1 because Z1 isn't necessarily real, right? So to break it down, you'll end up having this thing over here, right? So you see this 100 corresponds to this x1 only, right? And then you look at this y1, it's y, that's not to y1. y1 here, that corresponds to this I00, right? Because you can't multiply by complex numbers, so you have to compensate for that fact by having extra terms in your basis, right? And then you can see that very clearly pattern follows from here and here. And that's why you have these three things. You basically can see very easily that this is very clearly linear independent, right? Because since these terms, like obviously this term must be 0, right? If you multiply with 0, because all these other terms are always 0. Now the only concern is the fact this and this match up, but you just say that, well, you can't multiply by an imaginary number, right? So you always end up with something like x1 plus y1, which does not equal to 0 which equals to 0 if and only if x1 equals to y1 equals to 0, right? Because they can't clash with one another because they're moving in entirely different directions, right? So clearly it's in independence, and you can see that it's also a spanning set because I just did it for some arbitrary W. I never specified what the W was, I just said that it was in the set, and since it's for any W, it must be spanning for that regard, and hence dimension must be 5. Copy? Oh yeah, you should be able to get a copy of these slides on the Mathsoc website. I don't know when it's going to be uploaded, but yeah, if Abdella could confirm that for me. Yeah, right. And now we just go through, no worries, we go through an actual question. Oh, it's not actual question, what I'm saying. We go through the next part of the question. We consider two subspaces of W, this form, and now we want to find the dimension of U and V. Right, U and V. So let's just focus on U first. Right, we want dimension of U, so we do the same thing. We know that z1 plus x must be equal to 0. That just means z1 equals to negative x on I, which equals to ix. Right? So, if you were to go down here, so you just sub that term in, negative ix. Yeah, negative ix. Right. So all you do here is you kind of just do the same thing as before, which would be plus, and you just note the fact that this term here, you can't break it down, you can't keep it together, because obviously the fields are real. And you notice that this thing, you can factor out x, and x is a real number, so you can do this. And so you notice that there's 3 vectors here, and obviously they're linear independent. And so they span U as well, and so dimension must be 3. Great. So the important thing to note was that x is real because of the property from up here. Let me check. Here, because of this thing. Right, and that's why I was able to factorize it out and treat it as a scalar. You do the same thing with v, right? Just to make z2 the subject, you'll end up with this thing. And you can clearly see the same argument applies. So the dimension of v is also 3. Right? So we know the dimensions of the 2 subspaces now. Now, the question is, we want to find a basis for the intersection now. And from that, we want to find a dimension of u plus v. Now, if you recall from earlier, we just found u, or dimension of u, and dimension of v. So by finding a basis for u intersection w, we can find its dimension. And then from there, we can find this dimension, right? Because of the theorem from before, right? So it's dim u plus dim v minus dim intersection of u and v. Right, so just do that. So we want to find the intersection of u and v. Now, so every element of u and v must follow these 2 properties. Again, this is just a fact. If you read these properties, right? This is in this, right? I made z1 and z2 in terms of x because I know x is real. This is real, so scalar in our context, right? And since it's scalar, you can factorize it out, right? That's why I always made things in terms of x from that context. And you just kind of go with this. And now, if you were to sub it in to some arbitrary vector, so I'm just going to call it A, you'll see that very clearly you can just factorize it x, because all these things just depend on x, right? X, x, x. And so that means a basis for u and v is just simply this one vector, I minus 2, 1 on 2 I mean, and 1. Right? Because clearly it's the same argument as before. It spans and it must be linear independent because, well, there's only one vector, so it must be linear independent. And you can see that the dimension of it is actually 1, right? Because there's only one vector. And hence, we can easily find the dimension of the sum of the subspaces. Just sum everything in. Whoops, I should not have crossed it out. Sum minus 3 plus 3 minus 1 is 5. Right, so we found the dimension of the sum of the subspaces. It's not too much work because individually these things aren't too hard to find, realistically speaking, because it's mostly the same kind of process again and again. But the sum of the 2 subspaces might have been more difficult to find directly. Right, so that's why we kind of go this roundabout approach to find the sum of the vector spaces. Right, so that's pretty much vector spaces. I'll go through linear transforms. How far should I go in linear transforms? Okay, yeah. Once we reach like the 5 p.m. mark, we'll have like a 10-minute break. We'll see how far we're going to linear transforms from there. But again, this is also from first year, so it should be fairly chill as well. Right? So from first year, again, linear transforms is just it's a relationship between 2 vector spaces that has this property, or these 2 properties. Right? I guess the most important thing you need to be careful of is the fact that they must be over the same field. Right? The reason being is because, well, if they weren't, you wouldn't be able to have this second relationship. Right? If lambda was complex, but then all of a sudden lambda became real, it doesn't really make any sense. Like, yeah, you can't change the fields. It's probably something you need to keep your eye out in case they ask like a true or false question. Right? And the way you'll prove it is similar to what they did for what's that thing called? Subspaces, right? We'll just combine the two properties together to prove it at once, right? Because realistically speaking, you could have just straight up combined these two properties right off the bat, right? So that's what we're going to do right here, right? And it's not too bad to work with, so we'll go for an actual example. So we have the real, what's this called? Degree 2 polynomials, right? And we have the regular, what do you call this, 3D space. Right, and we want to prove this is linear, right? So to prove something is linear, you just need to consider two vectors from the domain and one scalar from the specified field, right? So the domain in this context is the polynomials, right? So we'll consider PQ from this set, and we're just going to consider lambda from the reals. The field in this case is implied because everything's in terms of reals, right? So you can introduce it unless they specify otherwise, right? So you just go with the obvious one first, right? And that's what I did here, right? Just list it out because you need to make sure that they don't undercut your marks because you failed to like state some basic fact, right? So make sure you state these things. And then now you just subbed in, right? So you just plug everything in. So P, well, just put P plus lambda Q. And then we note this fact that the sum of functions and derivatives are linear in nature. Alright, so what I mean by this is, suppose you have f plus g, t, well that's just equal to ft plus gt, right? And if you were to derive this, well it's just the derivative of them individually. Right. And since we have this property, you can just kind of split each of these things individually. This splits into those two. This over here splits into these two. And this over here splits into these two. Right. And now, since you want to prove that this over here is equal to TP plus lambda TQ, right? Essentially, you want to prove that the order of operations don't matter. You don't care whether you combine them individually together, then sub in, or you sub in, then combine. That's pretty much what you do. So you're going to focus on bringing all the P's together and all the Q's together. That's what I'm going to do. As you can see here, this is where the P's, so should underline, and this is the Q's. And you can very quickly observe that this must be TQ, because you just look at this thing up here. Just replace P with Q. There's obviously a lambda in front. And so you have this. Right, so these type of questions are fairly quick, right? The difficulty lies in the type of transformation they throw at you. But most of the time, it's usually just referring to something you already kind of know. Right, in this case, we know that sum of functions and derivatives are linear in nature. And so that carries on into this transformation. Right, but you just need to be a little formal about that. Right, from first year, we have the kernel and image. Really, the idea of kernel and image is just that the kernel is just the roots of a function. Right, so if you think of something like gx equals to 0, right? So this is essentially the kernel of G, right? Because it maps to the 0 vector in a sense, right? Image is simply a projection of the functions onto some other set, right? It's nothing too crazy there. And in turn, you can actually show that both vector spaces under the same field F. And the way you would show this, right? So how can we show this? It's basically the fact that you can use subspace theorem. Just straight up use the subspace theorem. And the reason why this might be helpful, like it could be helpful, is that it may reduce some of your workload. For example, if you can prove something is a kernel of something else, right? You may be able to prove that, you may be able to prove that it's a vector space by just noting it's a kernel. Because all kernels must be vector spaces, right? So you don't need to kind of go through the nitty-gritty details, right? Same thing with image, right? So if you kind of know that in the back of your head, it might kind of reduce your workload in very obscure cases, right? And this is a big thing from first year. I imagine everyone remembers the rank nullity theorem, right? I remember this thing. It was like from first year thing, yeah, rank nullity, right? The idea is basically the dimension of the image and the dimension of the kernel just add up to the dimension of the domain. And the idea isn't that crazy. It's really just that you can split. Okay, so with the description from before, every vector must either project into some other set or it goes to 0. Right? It's one or the other, right? So it's not too crazy to imagine that the dimensions of the two add up to the domain. Right? So that's pretty much what this rank nullity theorem is. And the usefulness of it is pretty much, if you know one, you know the other, right? That's pretty much one. And you end up having these three properties as well. You can prove invertibility. It's pretty much just invertibility, these three statements. Right? If the nullity is 0, so that means only the 0 vector maps to the 0 vector, then that means solutions are unique, right? So it must be invertible. Rank, well, full rank, it just means nullity must be 0, and hence you have invertible. Right? And now we'll just go through an actual example of this. Right? It's similar to first year. So we have this matrix, and we want to find its rank and nullity. First we find this, and then from that we may be able to find its image, or basis for its image. Right. So we just focus on the rank and nullity. So I kind of talked about what the rank and nullity was, but I never told you how to find it. In matrix form, it's really easy. All you do is you row reduce it until you find all the leading columns. Or you reduce it to, row echelon form. Right? And then you just count the number of leading columns. So just go through this. Right? This is just row reductions. Right? And this is like the most important thing. Because this, you can clearly see from here, you can't row reduce it anymore. Right? So, looking at that, you look for all the leading columns. So this is the leading column, because it's the first one that is the first row. And this is also the leading column, because it's the first one you see. And then you have a similar thing with 4 here. Right? 2, 1, and 2 aren't leading columns, because there's some column before them that has an element in the same row. Right? So this 1 from the first row column comes before the second column is 1. So it can't be a leading. So in blue, I'll just write blue, non-leading columns. And red is leading. Right? And that's what that's why I highlight over here. So you have 3 leading columns. So these 3 things here. And so the rank must be 3. Right? So the rank of a matrix is really easy to find, assuming you can row reduce correct. Assuming the process to row reduce is simple enough, right? And the nullity is just the number of non-leading columns, right? And the reason for this is because of the rank nullity theorem, right? Because the number of columns is the dimension of the domain, right? For matrices. So n equals 2. Number of non-leading columns. Right. Now, so you know how to do it for matrices. For more general kind of linear transforms, depends on the situation. But there is a way to basically reduce it all down to a matrix, right? Which is kind of why I did it for a matrix. I'll mention that later. But now, if you recall, one of the last part of the question was to find the basis for the image of A. And the way to do it is you simply just select the columns that were the leading columns, right? So you just look back to here. Let me just zoom out so you can see the whole thing. I selected the first column, the third column, and the fourth column, right, as my leading columns. All right. So I choose this vector, so which is this vector, which is this, and this fourth vector, which is that. Right. So all you do is you literally just kind of list them out, right? The only thing you need, so when you're selecting a basis, you just need to make sure you don't select columns that are the same kind of leading in a sense. So you can't do this. So for example, you can't do this because this one and here, they correspond to the same, they contribute the same thing overall, basically, is what that means. Right, so you must select this one. Right, so that's your basis. Right, for the kernel, it's a little more work. All you do is just do 0, 0, 0, 0, and then you just solve this. And then you sub in some parameters. In this case, there'll be 2 parameters. Right, that should be fine. Now, move on to this. Yeah, I'll probably make, I'll make this like the last thing, and then we'll have like 10-minute break before that. So, now, I mentioned earlier you can basically represent any linear map with a matrix. It's pretty much because if you think of linear transforms, it's like the properties are basically of a matrix, right? You have like the thing where it goes like ax plus b ay equals to ax plus ay, right? And the scalar thing where you bring the scalar out in front, right? It's very reminiscent of a matrix. And so what that means is you can basically just work with a matrix instead of a linear transform, right? But the thing you have to keep track of are the bases that you use. That's something you have to keep track of, right? And this is kind of just a notation, right? Just kind of the theory, right? You can find an equivalent unique matrix with respect to A. And this depends on your choice for the domain and codomain. Right. So the way you'll do this is from first year you subbed in, so it's basically you choose your basis. You sub in, so B here would be V1, V2, VP, right? Because here dimension of V is P. Okay, that's not the whole thing. Whoops, let me circle that again. Dimension of V is P. So that's why I'll go up to P. So what you did in first year is basically you just kind of sub things in, and then you represent it in terms of C. Right, it still applies here, so you just do the same thing. Right, find the coordinate vector, and this becomes your first column. First column of A. Okay, let me choose a different color so it doesn't blend in. First column of A. Right, and if you made this like 3, so this will be your third column instead, right? So just kind of make it shifted over according to whatever vector it is. Right, now that's fine and all. The only problem with this technique is that since you have to basically find a bunch of coordinate vectors, it becomes very cumbersome to apply directly. You probably felt this in first year where they did like, let's suppose, if you did some of the cheat questions, there was like a 4x5 matrix, and you kind of have to like reduce, you have to find a corner vector of some complex basis choice. You don't want to do that again, right? Well, I don't want to do that again for sure. So we're going to do an indirect approach, right? And to do this, we're going to use basically these two facts. The idea is these two facts just mean that if you combine two linear maps, it's also a linear map, right? So that's what this is. Combine two maps, linear maps is also a linear map. And it turns out the matrix of the combination of the linear maps is just the matrices multiplied. Right? Nothing too crazy there. So we do this with our original transform, but we break it down so that we have two identities. Right. Now, right now you might be like, why the heck would we bring identities into this? It's like, why complicate it? It's basically because if you think of the standard basis, it's really easy to work with it, right? Whenever you sub things into the standard basis, you can kind of represent the coordinate vector really easily, right? So, want to bring in standard basis. Right, standard basis is really easy to work with. That's why they are standard bases, right? And so if you were to transform individually, so step by step, so if I were to break down the process, it will be something like you have T, you have B, and you want to transform B to C through T, right, in your matrix. What you could do instead is, well, transform B into some standard basis, standard 1 through the identity. This is very easy to check because this is just the coordinate vector. And then next from there, you transform the standard basis into another standard basis through T. Right? Because since you're just dealing with standard basis, you just kind of sub in the coordinates. And then the third part, so I ran out of space. So this part here, you do identity to C. Right? This is just the reverse of the first case. Obviously, you're looking at different bases. So all you do is you find the inverse matrix. So you do inverse of, that's not inverse matrix. Right, an inverse matrix, you can just kind of say like, okay, I found this matrix and I put an inverse there. Right, so he can get away with that kind of thing. And each of these steps individually aren't too complicated. Right, you don't have to worry about like dealing with a bunch of coordinate vectors because individually these are very easy to find. And I'll go through an actual example so you see it. So we go through this question here. We have this linear transform, and it's the one from before. Right. And now we're going to represent it in terms of two bases. We're going to consider this one for the domain, and this one for the codomain. And now I want to show a matrix representation with respect to these two bases. Right. So I'll go through this. So the process I defined up earlier is pretty much this kind of matrix multiplication here. So B changes the basis from this thing to the standard basis of the polynomials. So it will be 1t, t squared. Right? Now let's see what's blue. So what S does is that it transforms 1t, t squared into the real standard basis. So this E3. Right, because this is the transform of T. Right, the middle one's always with respect to the actual transformation itself. The two outer ones are the identity transforms, just to make things easier. And this last one is, did I choose green yet? No, it's the inverse. Now, notice how I put inverse here. This is very important to remember. I'm changing from the standard basis back to C. So the final answer goes to C, right? Because you want to make sure it goes from this to this. Oops. Let me do that again. This to this. B to C. Right? So you want to end up at C. And the inverse is just because the matrix you'll end up having at the very end will be an inverse of some easy matrix you can find. Right? That's why I made sure to put inverse here. You have to make sure it inverses here. Right. So we'll go through this step by step. So we got the first one, right? We just change the basis from B to the standard basis of the polynomials. So that's what this is representing. So you have this one, and you want to transform to this thing. This is really easy, right? Because if you just look at it, it's the transforms the identity. So you just want to transform 1 plus t into S1. That's just 1, 1, right? 1, 1, 0. Because there's no t squared term, so that's 0. There's a 1 t term, 1. 1, what do you call it? Constant term is just 1. And you do the same thing for the second thing over here. So it's 2, 0, 2, 0, negative 1. Right? Because 2 plus 0t minus 1 times t squared equals 2 minus t squared. Right, and the very last one, which is red, here, is 3, 0. Oh no, 0, 3, minus 1. Right, same process again. As you can see, this matrix is very easy to find. You just kind of like, you pretty much just wrote it down as a row as columns. Right, you can do it in like 10 seconds. Right. So that's fine. So now we move to the second step. This is where we transform our matrix with respect to the standard bases. Right, and working with standard bases is generally easier. So what you do here is you just sub it in one at a time. T1, because that's the first one. So you sub in 1 into this thing, but then you know that it's just 1, 1, 0, because the derivative of a constant function is 0, right? And now you represent it with respect to this basis here, but then you know that E1 is just 1, 0, 0, E2 equals to 0, 1, 0, E3 equals to 0, 0, 1. So if you look at this, right, the coefficient term in front of E1 you need is just 1. Coefficient term in front of E2 is just 1. And this is 0. Right, and that's why you end up with 1, 1, 0. Right? So you do the same thing with the second element. So T. So just go through that. T. So you sub in, so PT equals to T. So P1 equals to 1. P2 equals to 2. P dash 2. Well, okay. P dash T equals to 1. So P dash 2 equals to 1. Right? And that's why you end up with this thing here. 1, 2. Oh no. Oh no. Okay, so it becomes 1, 2, 1 because of that. Again, you represent it as a corner vector, and you just end up with this. And you do the same thing with t squared, and you can very quickly verify you end up with this. Alright. And now, so we have the 3 columns, right? Because we used all the domain basis vectors already. So we have the full matrix. So all we need to do now is put it as columns, and you need to make sure you put it in order. So what I mean is I did T1 first, so that's the first column. I did T2, TT next, so that's the second column. And I did this one third, so this is the third column. Right. Yeah, so that's pretty much it, right? I guess I didn't mention this. I should have mentioned this. Sorry about that. You need to make sure your choice of basis is always in the same order. So what I mean by this is, I go back here. Wait, no, I go back here. Right? Notice how I did it 1t squared, right? You need to make sure when you do it here, it's also 1t squared. You can't change the order in between because it messes up your matrix. Right? And the same thing would apply to the e's. So if you look at this e thing here, when I do it from E to C, I make sure it's in order, the same order, right? And I do want to see. But then if you look at this, right, this is just the reverse of the first scenario. So if you recall, the first scenario was b2, 1, t squared. And I define this matrix of B. So I'll just do the same thing here. So I'll do C2, E1, E2, E3. Right? And I call this matrix C. And the way to do it is very straightforward. You just look at these vectors and represent it in terms of the same basis. But that's just the same thing in this case as listing them out as the columns. Right, so bam, bam, bam. Right, those are your columns. But since the direction is actually reversed, I invert it. Right, so you end up inverting it. See? And so we did all three steps basically. And now all we need to do is combine all three matrices. Right, so this thing brings it from B to S1. Well, actually, no, I should probably do this. Let me do this again. Oh no. B to S1. It's too far. S1. S1 to S2. And here, S2 to C. Right, so you can see the process as we go along. And this middle one is with respect to the transformation in T. This is ID, this is ID. So you can see how it transforms from B to C. So you just need to make sure it goes in the reverse order, right? So it goes from right to left. Right, and that's how you do this. Right, individually, none of them were very difficult. Right, so you just end up having three matrices. The general pattern is that this last one will pretty much always be an inverse. Right, so that should be fine. So for now, I'll let you guys take a 10-minute break. Or, yeah, 10-minute break-ish. Right, if you have any questions, just type in the chat, I guess. Yeah, I'll just, I don't know. Yeah. So, I think you should see a Spider-Man thing now. Yeah, you should see a Spider-Man thing. I'm just gonna mute myself for now because my laptop's going crazy. Right, so we're back. Alright, might as well start. Wait, I need to project the screen again. Should be up now. Alright, so we're going to start up again. We'll continue where we left off. So before we just kind of went through matrix representation. Now we'll be going over isomorphisms. The idea is basically, well, you know T is a transformation, right? It's a mapping, or a function essentially. So the concept of invertibility isn't that absurd, right? So if you have an invertible, you can say two linear map or two vector spaces are isomorphic to one another. So essentially they're kind of the same, right? Because you can find a one-to-one relationship between the two, or for each element. Right, so just go through a quick example. So we'll consider two vector space pairs, C2 and R2, under the field R, which is person, and we want to consider whether this is isomorphic. I think I forgot to write that somewhere, but that's the idea of this question. Right, now if you go down here, I already kind of spoiled it before, but the idea is that these two can't be isomorphic. The reason being the dimensions of the two vector spaces are different from each other. Right, because the dimension of R2 equals to 2. Right, and if you think of the linear transform, right, you're essentially going to have a matrix. So from here C2 to R2. You know every linear transform has a corresponding matrix. So I'm going to call this A. This matrix here must be in 4, 2. Also 2, 4. I forget. 4, 2, 2, 4. 2, 4. I think it's 2, 4. 2, 4. Reals. Right? Clearly this matrix can't be invertible because, well, it's not square. So in turn, this mapping itself can't also be invertible. Right? So that's kind of how you'll say it in this case. Now, the second one over here, so they can't be isomorphic. Now this first one, or the second one, you can see that the dimensions are the same, right? Because this is literally kind of something we've seen multiple times throughout this kind of seminar. Its dimension of this thing is 3, and so is this. Dimension of R3 is 3. So the dimensions match up, right? So you can't use the same argument as before to disprove it. You have to go a different way if you want to disprove it. But if you recall from earlier, we considered a linear transform from P2 to R3. Right? So, and we can also consider this matrix here, essentially. The reason being is because these two parts are both invertible anyway. So you need to worry about the middle part, essentially, for this one transformation. And it turns out, if you go down here, that, because that's what this circle thing is, I found a determinant of it. It's actually 1, it's non-zero. So that linear transform was invertible. So there does exist a linear transform which is invertible. So hence they must be isomorphic. There exists some invertible linear transform, so isomorphic. Right, they must be isomorphic to one another. Right. And you have to be careful. It just there has to be there has to be some linear transform such this is true. It doesn't mean for every linear transform that this is true. Right? That's something you have to be careful of. But we'll move on to invariant transforms. This is also something new. Invariant transforms is, the idea is basically, if you have some sort of subset or subspace, I guess, some subspace, and you were to map this subspace through some linear mapping or transform it, and it turns out that the image of the set is also of subspace of X, right? So it still remains inside of X. So what this means is Tx subset of X. So it maps back into itself, or a smaller subset of itself. Then we call it invariant under T. Right, it's invariant because you don't ever leave the set after transforming it. Right, so the status pretty much stays the same. Right, or it becomes smaller. Then that. So now we go through a question. So the way you prove invariant transforms is basically you will note the key property of the set you're looking at, and then try to prove that the transform still maintains that property. So this is an example here. V vector space, S and T are two transformations from V to V. And now we're going to consider W, where it's the kernel of this subtraction of subset of linear maps. If this property is true, then we want to say that W is invariant under T. Essentially what this means is you want to show that TW is a subspace of W. Right? So you want to show that W stays within, well, the transform stays within W. So pretty much this. And the subspace part comes from the fact that it's an image of the transform, right? So that's fine. Okay, so we consider any W in, well, any vector in the domain, essentially, this thing here. And we want to show this transformation is also in W. So essentially what that means is we want to show W in kernel of S minus T implies TW is in kernel of S minus T. Right? And for something to be the kernel of some linear transformation, that just means that kernel, oh whoops, that's not what I meant to write, S minus T, TW is equal to the zero vector as well. Right, that's all it means for something to be in the kernel, right? So we will focus on what this is. We will prove that this maps to the zero vector, right? So we'll do that. So we just sub it in. And then we kind of just break it apart because we know that linear maps are linear when you do the operations, right? Functions are linear. So I can break it up here. And over here, we use the assumption because they tell us an assumption, right? So you're probably going to have to use it. So I use it here. So TS, or ST, I guess, is equal to TS. So it's reverse. So they commute, doesn't matter the order in which you use sub in the linear model, or no, linear transforms. Do this. And the reason why I do this is because I noticed that if I do this, the T's are essentially outside, so I can factorize it out. And you'll end up with a T minus S. Here. Sub in W. But then what was W again? Right? We remember that W is in the set here, but the set here is the kernel of S minus T. Right? And that's the same thing as the kernel of T minus S, because, well, it's just minus 0, minus the zero vector is still the zero vector. Right? So what that means is this thing must equal to the zero vector. Right? And now any linear transform applied to the zero vector is also the zero vector. Right? Because of this property here. 0x equals to 0tx equals to zero vector. Right? And hence we have shown that this thing does map to the zero vector, and hence we have shown that, and then actually cut off, unfortunately. But yeah, the idea is we have shown that this is true, and since it's a mapping, since image of T, that implies that what do you call it? Image that this is a subspace as well. Since it's a subset and it's a subspace, it must have this property. That's fine. Right, and that's how you show invariance. Right? Invariance, you just consider what the property for set element to be in the set is, and just work around that based on your assumptions. The normal form. This is kind of something I'll just kind of breeze over. The idea is basically it's just the matrix representation. But you choose the basis for the kernel, extend it, and do the same thing for the image. And it turns out you can actually have just this kind of representation. Right, just extend your basis for the kernel to include those vectors, and you should have these. And then you just choose the image basis vectors to be the transforms. So it'll be TV1, TV2, etc. Right? And since it's a transform of itself, right? So you do TV1 of C. This is obviously going to be 1, 0, 0, dot, 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 0. Right, same thing for the second one. So 2, 0, 1, right? Because basis. Itself, and that's why you have this identity kind of diagonal shenanigans. And these zeros correspond to the fact that not full rank. Wait, is it not full rank? Yeah, not full rank. Right, that's what those zeros represent. Right, so I'll just go through that. Now, we will introduce this concept of similarity. Right now, in this part of the course, you're not going to need okay, actually no, wait, let me say that again. Similarity is a property that you don't prove so much as you want to disprove. Right? To prove it, you need Jordan forms or something like that. I forgot, but that's the second half of the course. Right? But right now, we just note that the idea is you can represent a matrix as kind of an inverse matrix times another matrix. Right? And we say they're similar. Right? The key idea is just they're essentially the same transform. You just choose a different basis. Right? And since they're pretty much the same transform, they will have some properties that are the same thing anyway. And these 4 properties are the rank, the nullity, the trace, and the determinant. Yeah, should be fine. Yeah. None of these are particularly difficult to remember, right? So whenever you want to disprove 2 things are similar, let me say again. Whenever you want to show 2 things aren't similar, you will look at these 4 properties and try to find a mismatch. Because if there's a mismatch, obviously that means they can't be similar. Right, so we consider this. Here's an example. We have 2 matrices. Oh wait, I should mention this. They must also be the same, they must be square. Yeah, I forgot to mention that. They must be square and also of the same size. Because if they aren't the same size, obviously they aren't the same representation. Right, so I'll go to that. Here. So we want to prove they're not similar. So we'll go through the easiest one first. Right? So you look at these 4 properties up here. The easiest one to me is definitely the trace, because that's literally just adding the diagonals. And the next easier thing is probably the determinant, because I don't have to row reduce, because I notice there's like a 0 here, 0 here. And rank and nullity are kind of more annoying, I guess. But if I have to go through it, I'll go through it. Actually, no, you only need to go through one of them. Rank, and the nullity just follows through afterwards anyway. Right, so we go through a trace, looking for a mismatch. The trace here is 1 minus 2 plus 1, which is 0, minus 4, 3, 1. This is 0. Right, they're the same, so we can't disprove the fact that they're similar. So we have to keep going. So the next easiest thing is the determinant. And it turns out when you just do the determinant on this thing, so you go here, and here, and you just get this thing. It turns out that they're not equal to one another. Right. So that's just first year determinant calculations. And since they're not equal to one another, you can say that, well, one of the invariant properties aren't equal to one another, and hence they can't be similar. Right? So can't be similar to each other. Because if they were, all the properties must match. right? It's like a proof by contradiction kind of thing, right? And that's pretty much all for linear transforms. We'll move on to inner products, right? So the idea of inner products is just that, well, it's just an extension of dot products. It's really, that's all it is. Like, dot products is this thing. Well, we're going to extend that because it's quite a nice property, right? So we have complex. Complex, you just conjugate the first one, right? That's how they do it in this course. You have to be aware of how to do it. It might change in different courses, but in this course, it should be the first one that's conjugated. Right, and the dot product has this interpretation where you have the angle in between two vectors. Right, this is from first year, and if they're zero, then we say they're orthogonal to one another. Right, we'll also carry this property forward to inner products. So if the inner product is zero, like you have these four properties, right? These four properties aren't too complex. Right, it's linear in the second term. Well, okay, it's linear in the second term. You can bring out the coefficient in the second term. The biggest change is this thing. So it's not symmetric anymore. So if you want to sort the order, you have to conjugate it now. Right, so you have to be aware of that. It's the biggest change. Biggest change from dot product. Right, just be aware of that. And I mentioned earlier that the idea of orthogonality is extended to this. Right, we do the same thing again. So if two vectors are orthogonal, well, okay, if the inner product is zero, we say they're orthogonal to one another. Right, same idea as before. Right, inner product, dot product, just replace the words. Orthonormal, well, these vectors are orthogonal to each other, but the the norm is equal to 1 if they're the same vector. So essentially length is 1, so you normalize. That's why there's normal in there, right? Nothing too crazy there. And this is another thing why we want to generalize dot products. It's the idea of projection. So if you recall from first year, projection is that thing where you go like, okay, this is vector, right? I have this vector that I like, and this is vector that I have. I want to represent the vector that I have in terms of the one I like, in a sense, right? So it's this thing, diagram. You want to find this part here, right? So it's pretty much the same thing. Instead of dot products, it's inner products, right? And I guess the order is important in this. Yeah, the order is probably important in this. So the way you remember it, just make sure X is in the first one, so the one you're projecting on from. Right, so this is in this context, let me lay this out. This is Y, and this is X. Right, so Y is over here. It's this blue one. Should probably change it blue. And this is X. Right. And the idea of projection is that you find the part that's explained by Y. Right, just that. And I'll go for an example of this, how you calculate it. So let's suppose we have these three vectors, or three functions, polynomial functions. And now I want to find the projection of f onto W, so the span of these two, using this inner product. Right? Now you can clearly see, the first thing you'll note is that this is for a degree 2 polynomial space. So the dimension of the degree 2 polynomial space is 3. That's not 3, that looks like a bracket. It's a 3. Right. The next thing you'll note, the thing you want to project on contains two polynomials, and they're clearly linearly independent. Right, look at these two, right? So obviously, because this has a t-squared term, to get rid of it, the coefficient must be 0. The only way this thing is 0 for all t is if the coefficient is 0. so they must be linearly independent. And the inner product is some weird shenanigans that they tell you. You don't have to prove this inner product, they just tell you it is. So noting the fact that our the thing we want to project on, has two vectors, and the whole set, or the whole vector space, is dimension 3, there's going to be a third vector, right? It's going to be a third number, or not number, third polynomial, and I'm going to call that ht, right? And I'm going to say that h is in the complex, what do you call it? Orthogonal complement of w, right? And why can I say this? Right? It's kind of important why I can be able to say this. The reason why I'm able to say this is because it's pretty much from the future theorem. It's called what's that called? Graham-Schmidt process. It's pretty much from this thing. Right? So if I find a third vector, right, I can just find the orthogonal variation of it. And clearly, if it's orthogonal, it must be linear independent. And since it's linear independent, there's 3 vectors. So it must be a basis, right? Because the dimension is 3, right? And since we want the projection of f onto w, I pretty much just want to find what. Okay, do I have here? Okay, now let me just get rid of some of these things. You want to find alpha 1 and alpha 2, these constants. So the parts of f that are explained by g1 and g2, because g1 and g2 are in w. And the way I'm going to do this is that since there's 2 constants, I'm going to inner product twice with 2 things, right? And the only 2 things I can inner product with is g1 and g2. Right, because I know h is orthogonal to both of them. Right, so it will get rid of the h for me. So as you can see, the h disappears. It's like plus 0, plus 0. And you just solve these simultaneously. So now all you need to do is find what these inner products actually are. And that's what this process is. So f, g1. So if you look at what f is this. So you just sub in f over here. So f0 is 3. And then f1 is 4. f2 is 7. And you do the same thing for g1. So g0 is 1. g1 is 0. And g2 is minus 1. Right? And then you just sub all those numbers in according to this inner product. And then you found the inner product, right? Just sub numbers in, you found this. Do the same thing for g1, right? Obviously this one's positive because it's the same kind of thing. So it's like a norm. Positive, that's fine. g2, g1, that's fine as well. Right, again, just summing numbers. And then, so that gives us this one. So now we need to find fg2, right? So we do it with respect to g2. So we go over here. And I'll just do the same thing, just sub in numbers. Now the important thing, I guess, is this one. These other two are pretty much the same thing anyway. The idea is that g2, g1, if you want to find the reverse, you just conjugate it, the whole thing, so conjugate 2, and it's just 2. Right, I guess that's the most important thing from this. You could find it again, but then that might as well just kind of use that property of inner products. And you just sub numbers in from here. So using all these numbers that I found, you kind of just sub it into the num earlier. So you sub in fg1. Okay, g1 is -4, right? And this is 2. It's 2. Oh no, that's not 2. This thing's 2. And this thing here is 2 as well. So just go down here. You can see it's 2 alpha 1, 2 alpha 2, minus 4. Do the same thing for this, just kind of sub numbers. Solve simultaneously. You'll see alpha 1, alpha 2 are these values. And then from there, you just sub in the fact that projection of f is minus 5g1, because alpha 1, alpha 2, so 3, g2, and just sub it in. Alright. That should be fine from there. Now, if you go down, that's how you do that. Now, this is the Gram-Schmidt process. This one's kind of a long one. It's kind of cumbersome, but once you need to do it a few times, but it's not too bad. The idea is basically you just procedurally do it. So you start with one vector, then you build off that vector, and then you build off and build up. Right, build up one at a time. Right, so let's go for example. And the reason why it works is because you're making sure it's orthogonal within each step. Right, so this step here, make sure W1 is orthogonal to W1. This step here, make sure W3 orthogonal to W2 and W1. Right, and just keep doing the same thing. Right, so I'll go through an example. So we'll go through this question here. We have 3 vectors. Right, and now I want to find an orthonormal basis for W. Right, so that's what the Gram-Schmidt process was made for, right? It's made to find orthonormal basis. So we go through this approach. So firstly, we just choose our first vector, right? This one's easy. Just choose which one works with you. I just choose the first one because it's literally the first one I see, so I'll just go with it. Now, this is kind of where some work has to be put in. V2. Now, I want to find the second orthonormal vector, or orthogonal vector. So, I do this, right? Just write out what the formula is, right? So, I do V2 minus the projection of V2 over W. Notice that's W, right? It's not V. The things you're projecting on is on W, right? And then I just sub in all the numbers. Right, this is just the projection formula. Projection formula. And from here, you just inner product, or dot product, I should say, in this case. And then you find the coefficients. Coefficients, as you can see, and you just kind of sum things up. And eventually, you'll see this. Well, I'm not going to go through these calculations. They should be very straightforward. Right, so I found W2. Now for W3, so if I'll go here, you're going to need to project on W1 and W2, right? So I did up here, what this over here was just some intermediate calculations. Whoops, that was not meant to cross out. Intermediate calculations. Right, you can check that in your own time. But yeah, just sub in those numbers. And then eventually I'll get this. Right, the important thing to note is that the thing you project on is the W's. Right, so if you had Wn, you project Vn onto W1 all the way to Wn minus 1. Right. And make sure this thing here matches, so V3 minus everything else. Right, and if you look up here, it was, oops, okay, it's not appearing, V2 minus. Right, so make sure the subscripts match. And here you have your orthogonal basis, right? I found 3 vectors, and that's all the vectors I need because the basis only had 3 vectors to begin with. So all I do is I just kind of put them into here, right? And this is the VW2, and this is W1. It's W3. Now, go down here. If you want to find an orthonormal basis, which is what the question asks, all you do is divide by the length. So you look over here, or the norm. So this thing here, W1 is square root 2 squared plus 1 squared plus 0 squared. I just square each term, right? That should be square root under the whole thing. And this turns out to be 3, because 4 plus 1 plus 4 is 9, and that's 3. So divide it by 3, which is this. Do the same thing over here, you get 1 on 9. Same thing here, 1 on square root 1 on 1. Right, so the last step is easy, just make sure you divide by the norm. Divide by norm. Alright. Okay. Well, okay. So that's how you'll do the Gram-Schmidt process. It's really just making sure that you project onto every other vector you found before, right? So W1, W2, and then making sure you keep the signs and stuff consistent, right? It's very easy to make a mistake in this type of questions because there's a lot of calculations involved, but that's just how it is, unfortunately. Now we'll move on to QR factorization. We're nearly near the end of inner product spaces. I don't know if I can go for group theory at all. Let's see. Okay. So the idea of QR factorization, to put it simply, it pretty much just comes from the Gram-Schmidt process, right? Because you end up having a bunch of vectors, and you could have a bunch of coefficients with those vectors. Let's put into all this is. Alright, this result comes from that. And the important thing to note, I guess, is that the matrix you're working with has to be full rank. Right? The reason why it has to be full rank is because if it weren't, it means that your columns aren't actually a basis. Right? Means columns form a basis for col A. Right? That's all that full rank means. Right? So you can use the Gram-Schmidt process from before. And this is kind of the representation. Q1 all the way here. The pattern is very straightforward. Here, you just note the fact that there's, well, Q vectors that you find from the Gram-Schmidt process. Right? So it's the Gram-Schmidt all four normal vectors. Now, the thing you need to remember here is the fact that this first row corresponds to the first vector from Gram-Schmidt process. Right? You notice how it's Q1, Q1, but the thing to note is that the diagonal elements is the, what do you call it? Pre or full normalized version. Right? So the diagonal elements are the lengths before you normalize them. So that's why it's good to keep track of what they are beforehand. Right, it's also the reason why we don't normalize on the go. It's so that you can just kind of look at it and figure out what the length is. Right? And you see this one? So it's the second vector now, and here this would be the Q vector instead. The other thing to note, A2 and AQ just refer to the columns of the original matrix, A. Because if you think of A, right, it's just A1, A2, AQ. Right? Because it's a P by Q matrix. P by Q. That's how it was defined originally. Up here. Where is it? P by Q. Right. And that's how you do it. I'll kind of skip this, but it's very straightforward. If you want to make a square, just finish the columns. So extend the basis for the columns, and then just add a bunch of zeros to make the diagonal matrix work. Right, so QR factorization of this. Okay, so you need to list out the column vectors as your B1 is 1, 2, 0, 2, and B2 in this case is the second column 2, 1, 1, 1. Transpose. Right? And so these are the vectors we start off with. So W1 is this, so we just choose it as the first vector because we need an initializing point. And from here we just do the Gram-Schmidt process on it. So we work with the second one, W2, and we do B2 minus the projection of it onto the previously chosen basis vector. Right, and just go through this, and this is just kind of calculations, and here you end up with this. Right, the next thing you'll do is you'll look at the third column and do the same thing. Third column, third column, third column. And then you project it onto the first and second vectors that you found through the Gram-Schmidt process. Right, and that's just sum things in, and you'll see this. Alright. Now, since, if you recall, we have to normalize these things. So all we do is find the length of, so I'll just do W3 because it's the closest one. You need to find the length of W3. So if you look at this part here, it's the same. I just multiplied it by a factor so that the length is 1 now. Right? So you can easily find that. So this is square root 4 plus 16 plus 9 plus 25. Right? All I did was square each term, and that should be 29. Wait, did I square correctly? Yeah, I did. Okay, 29, 54, so 3 root 6. Right, and that's what you see here. I ignored the 109 because the 109 pretty much cancels out anyway, so don't worry about it. Yeah, should be fine. Right, and so now these Q's become the Q matrix. Right, all I did here from this point to this is that I made it all divisible by 3 square root 6. Right, 3 square root 6, 3 square root 6. So I can factorize it out. Right, because I don't want to have fractions in my matrix because that looks ugly. Even though this looks kind of ugly, but it's fine. And all I did to do that was multiply by square root 6 and square root 2. And if you look at this thing here, that's the first column. And if you look at this thing, it's the second column. Right, and do the same thing here, third column. Just keep going like that. Now, so you found your Q matrix, right? Now you need to find your R matrix, right? Because remember, it's QR representation or factorization. So for the R matrix in this case is W1, right? So this is corresponding to the first vector. So it'll be Q1, B2, Q1, B2, Q1, B3, right? And this is W2, and this is Q2, B3, and this must be W3. Right, so the first row is the first vector you found in your process, or your Gram-Schmidt process, second vector, and so forth, right? And just look at the columns corresponding. So this is column 1, diagonals are exempt, so this is column 2, column 3, so B2, B3, third column, B3. Right, and just kind of plug in numbers here. Right, so Q1 was what we found here, B2 is literally just the second column of the original matrix. Right, so if I go back here, it's not showing up. Right, so 2, 1, 1, 1, second column, and you'll see it's over here, 2, 1, 1, 1. Right, and that's how you end up with this. And you do the same thing for these remaining elements. And eventually you'll see that this matrix is what you end up with. Right. And so all you do is, well, we found the Q part, we found the R part. You just combine them now. Right, so this is Q, and this is R. And hence that's our QR factorization. Right. Right, so Oh no, there's still adjoint. Okay, yeah, I don't think I can go through group 3, unfortunately. The slides will go up, right? But yeah, I can only finish up to, what's that last one called? Least squares. Right. Unless I go over time. So, the idea of adjoint, so it's still in linear maps. Oh well, okay, we're going to consider a linear map. An adjoint is essentially kind of a reverse operation with this unique property. Right? You're mapping from W to V, and it has this property where the inner product has this property where you can just kind of swap it. So you have TV, W, and now all you do is bring the T over to W, right? And you isolate the V. Almost. And that must be true for any combination of V and W. Right. And they have some properties here. I'll just skim over that. Now how would you find this adjoint? Because right now we just kind of described it. The way you find it depends on how you define the inner products. Right? So in this question here, we have this linear map and we have these two inner products. Right. So we have the standard inner product for R2 and we have this polynomial inner product for P1. Right. So what we do is we note that we want to find, what's it mapping to? P. So P, T, X equals to T star P, X. Right, all I want to do is bring the T over and make an asterisk. Right, so you firstly note what type of inner product the first one is. This is in terms of T, so it must be this one. Right, it's in the codomain. So you end up having the polynomial inner product. And this first one, or the second one, corresponds to the standard inner product, so the dot product. Right, you need to know what type of product you're working with so that you know how to break up your answer. Right, so we go with this. So we just consider two random representations and we just sub them in. Right, Tx looks like this. And since the polynomial inner product is just subbing in and then multiplying, that's what I'm going to do. Sub in 0, you get this. Right, 0, 0. And 1 is just minus 1. Right, so minus 2x, 2, and you get this. And then for this here, it's just sub in 0 into this thing. And sub in 1, it's just this thing. It's not erasing. Okay, yeah, there. Right, so we know this, right? But we want to represent it in the form of, I'll write it again. We want to represent Tx P equals to X T asterisk P. And this is in the standard dot product. Right? And we know the way the dot product works is by the fact that we do x1. Okay, so let me do this again. X, y is just x1, y1 plus x2, y2. Right? You literally just match up the coefficients. Right? And so if you look at this part here, you see this x1 and there's an x2. So I'm going to split things based on that fact, because I know that's how my inner product should work. That's what I'm going to do here. x1, x1, bring it out here. You end up with this part here, x2. You end up with this. Right, simplify, do some addition and stuff like that. And eventually you end up with this. But we know this is also an inner product of these two. And hence, that must mean T asterisk P is equal to 2P0 plus P1 minus P1, where P T equals to P0 plus P1 T. Right? Because I never specified what P0, P1, and X x1, x2 were. I just said there were some numbers. So in general, this must be the form they represent. Right, so this is kind of just recognizing that fact. This. Right. That's what this is. Right, yeah, I just finished this off. Okay, so we consider, so that's what an adjoint is. That's how you find adjoints. You have to consider what type of inner product you're working with. And from there, just kind of break things down so that you get the answer. Now, since we know what an adjoint is, there's going to be some properties related to adjoints you have to consider. So we have some special properties. So we have something called unitary, isometry, and Hermitian. Right? Unitary, it just means the adjoint is the inverse. Hermitian just means self-adjoint. And this one, isometry, it's kind of weird, I guess. Is it 4V? Yeah, it just means it keeps the length, right? It doesn't alter the length itself. Right, and it turns out there's some kind of properties that are equivalent. This is in your slides. I'm not going to really go through this. Now we'll go through a question where we consider those properties. So we have a linear map, and now we want to ask, is it unitary, isometric, Hermitian, right? And if you recall earlier, all these properties are related to the adjoint. Everything's related to the adjoint. So you need to find what the adjoint is first, right? So that's what we're going to do first. We're going to consider x, y. You find the adjoint, kind of just sum everything in. You know tx is this form, so you just reverse and put a minus in front. Right? So it goes tx1, x2 equals to minus x2. Whoops, minus x2. x1. Right, that's what this is. And you just dot product them. Right? Because we're dealing with the complex dot product. Right? Notice how I put a bar on top of these two. And then since I want to find this form here, I remember that the dot product is x1 bar y1 plus x2 bar y2. Right? So let me get rid of this. x1 bar y1, x2 bar y2. Right, so you have these two. And what happens is, since I want this, I rearrange it so it looks like this form. And so that means t star y must equal to this, then this. Right? Because that's what the dot product is, the complex dot product. Similar technique as before. Right? So now we know the adjoint, and so we can actually say things about whether it's unitary, isometric, or Hermitian. Right. So let's suppose, now we're going to the first one, right? Unitary. So what unitary is that it means that the adjoint is the same as the inverse. Right? But if we look at the inverse, right? If you invert this, you can clearly see it is invertible because it's 1-to-1. You can it's kind of easy. You can kind of see it from this. You just kind of reverse minus. And it turns out that if you were to inverse this operation here, you just kind of do a reverse here. So we know that TWZ or TXY, I should choose XY so it's less confusing, equals to minus YX. So T inverse minus YX must equal to XY. Right, that's just what inverse means. Right. Now, all I did here was replace Y with minus Z and X with W. Here, you see? So it becomes W minus Z. Right. But then you know from before that t, the asterisk, or the adjoint, is the exact same thing. You just reverse the order and you minus the second term. Reverse order minus second term. So in turn, that means the adjoint and the inverse are the same, and hence it's unitary. Right. Now isometric is the second one. Now this one's easy because of the theorem that I kind of skimmed over before. We know unitary is equivalent to isometry, so it must also be isometric. And Hermatian, in this case, we know that t asterisk xy equals to y minus x. Right, so if you want to show that it's Hermatian, you need to show that t equals to t asterisk, or the adjoint is the same, self-adjoint. You can clearly see that, if you look at these two, right, they're not the same, so you need to give a counter example, because this actually just turns out to be just a minus of the same thing. Right? So I consider this vector here, t1, 0, just reverse minus of 0 is just 0. But then we know that the adjoint of 1, 0, you reverse it, but you minus the second term this time. So that's how you know this. And these two are clearly not the same. Hence, it can't be Hermatian. Right? Because it's not true for every vector. Right. And that's how you would go about showing what type of linear map this is. Right. So now, this is the last thing, or 2501 basically, the method of least squares. The idea is basically, well, you have a few unknowns. So let's suppose you have 3 unknowns, but you have 7 equations. Right? It's possible that you won't find a answer that fits all equations simultaneously because there's so many of them. So you need to work with something that's the best estimator of it. And the way we're going to do that is by least squares. And it turns out it's just this, right? A asterisk in this context just means complex conjugate transpose. Wait, I should just say conjugate transpose. Conjugate transpose. That's what A asterisk means in this case. Right. And the way you'll do it is, as you can see here, you want to find the solution of x. So you need to set up your A star A and your A star B. Right? This becomes a vector. And this is a matrix. And then you just row reduce to find the answer. Right? So the question is, how do you find your A first? Right? Because the B and A, that's kind of what you need to find first, and then you can find everything else. Right. So in this case, you have this function here. You want to fit these 4 points as best as you can to a linear function. So what you do is, you'll notice that you essentially have AB equals to Y. Right? Because this is your matrix, and you can just kind of observe that 1, 1, 1. Because remember, in this function here, it's always A, it's always constant. So now you just need to write your x points for the B's. Right? Because you can see here, Bx. I'm going to make it dependent on the position. Y2, Y3, Y4. Right. And yeah, so all you do is write out the terms. So this is Y1, Y2, Y3, Y4. And correspondingly, there's an X1, X2, and X4. Right? And that's why you end up with this. Right? This first term corresponds to the rows. of the column, the second column I should say. And this part here, 6, 2, -1, 7, is this column vector. And you have to make sure when you do this that they correspond. So -1, 6 is from this first one, right? So they're on the same row. They match row-wise. You have to make sure that happens. And from here, you just find the conjugate transpose. In this case, it's just the transpose because there's no complex numbers. And you just find the answer, just multiply. And now you need to find A star Y. Right, because the solution you initially want to solve is y equals to ax. All you do is multiply both sides by asterisk y. And then you invert to find x. Solving, and you find x from that. Right. So that's pretty much all for inner products. Right, because from this point onwards it's just inverting and stuff like that. Alright, so that's pretty much all for 2501. Do you guys think, wait, should I go back to group theory for 2601? Or should I just end it here? Let me go. Thank you guys for coming. So 2501 ends here, basically. Right, and if you want to kind of like look at the calculations and all that, it should be on the website for Mathsoc later on. Right. I guess I can go real quick over group theory. Oh, just do it anyway? Okay, yeah, I'll just do it. Okay, so the way I initially kind of set it up was that I'll go through group theory first, but then I kind of realized that group theory is only 2601. That's my bad. But it's right. So I'll just do what group theory. I'll do it real quick. I won't go through I'll just go through examples. Oh yeah, I'll just go through examples then. Okay. Suppose so you have these kind of 4 properties, right? Groups are in a sense a basic version. We can skim through. Yeah, just go through examples then. Yeah. Right. So the most important thing is how you approve these things. Right, so you read the question and stuff like that. You find the most important property. So for this question, for example, you suppose G is a finite group, for example. And now you want to show that there exists some positive integers such that any element, because keep in mind it's some arbitrary element, will eventually map back to the identity element. This makes sense, right? It's not too hard to imagine because if it's finite, like you can't just keep, you eventually have to reach a loop. So that's going to come up in your argument somehow. But you have to make it more formal. That's kind of the challenge of this question, in a sense. So since it's finite, you're going to use that property. You're going to say that the group size is some number, m. And I'm going to consider some integer greater than m, right? And some random element in G. And I'm going to consider the multiples of A, right? And by the closure property, they must all be in G, right? Right. The reason why I consider some k greater than m was because of the explanation earlier. We know eventually it must loop back, so that means like eventually you're going to have to reach the same point. Now, this is kind of where the finite part kicks in. G only has m unique elements, hence there must be some integer. Well, I'm going to fix I greater than j for convenience sake, really, such that it loops back. Right? Because if this weren't the case, then you're saying that there are k different elements, but that contradicts our initial assumption of it being m unique elements, because k is greater than m. Right? So we'll use that fact. Yeah. And now, as every element in the group has an inverse, you just kind of times both sides by the inverse of this element. I did skip some notation. this A minus J is pretty much just A minus times A minus times dot 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 A minus J times. Technically, that's what it is, right? And that's why you can multiply both sides by it. And then you'll see that you'll end up with A times dot 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 A I minus J times, right? Technically, that's what's going on, because you can't just, because right now it kind of just looks like I'm just bringing the powers in. So yeah, when you actually write the argument out, you should be more specific in that kind of way, right? And since I is greater than J, clearly there must be more than 0 elements here. And so the power must be greater than 0, so it's a positive integer. Hence, I found some positive integer such that the element maps back to the identity. Right. And you can see that this is true for any A, because I never specified what A was. But the choice of I and J would obviously change depending on it. Right. Fields. Fields is just, it's a group, but with 2 operations. You have to prove that one is abelian under addition and abelian under multiplication, where you remove the addition identity, additive identity. Right. And yeah, that's pretty much it. So it's pretty much the same kind of thing. And now, this is subgroup theorem. It's very similar to the subspace theorem. It looks very familiar to it, in the sense that you only need to prove a subset of properties are true, and then you can prove it's a group, given that it's a subset. Firstly, it needs to be non-empty, and you have these 2 things, closure and existence of inverse. Right, pretty much the same as the other one. So, go through this question. We have this group. Oh, okay, whoops. We have this set. And clearly, HB is a subset of G. Right, you can clearly see that. The reason being is because G is a group. And these elements here, since it's a group, must also be in G by closure. And so all these things must, the whole set must be in G. Right, that's fine. And so the first thing you check is that it's non-empty. Just make A equals to E, and clearly E is in HB. Right, because you get B0, E0, B inverse, and that equals to B, E. Right, so that's fine. Now we need to prove the 2 other properties, closure and existence of inverse. So I'll do that right now. The closure argument is basically you have to do it for some arbitrary choice of x and y. Right, so, and we know the form of x or y must be B, A, B inverse, where the middle term is some element in G. So you do this is that. So I made sure that A and C are some other elements in the group. Alright, and now since I want to do closure, you just combine the 2. So you do the operation on the 2 elements. And just do it here. And then this part you need to be careful, I guess, because like you might skip steps, right? You might feel like you'll skip steps because it's so simple in a sense. Like for example, this part here, right? I just rearranged the way you do the operations by associativity, right? That's intuitive, but you need to write out the reasoning because they're testing you on that, right? Here I kind of combined 2 steps. Here I noticed this was the identity, and the identity with any other element. So Z is the Z element itself. So that's kind of what I did here. Right, kind of just skip that part. Right, I think that should be fine. Skipping that should be fine. And here I use the associativity argument again, so I can bring this A and C. The reason being is because since you want to prove that it's closed, you want to basically find something in this form, where this A thing is some alpha in G, right? So the 2 outer terms must be B and B inverse, and you end up having this A0C, and that must be in G, because we know A and C are in G, and since G is a group that's closed under this operation, that means they're the operation of the two must also be in G. Right? Hence, we have, what do you call it? So we have some element that's in G, and it's in this form. Hence, it must be in HB. Right? So the joint operation must be in G. Or HB. That's my bad. Right. Yeah. And inverse is basically, you just need to show that as inverse. The actual calculation is the same in between, except now you have to be very specific as to what elements you're choosing. Right? Before I chose X and some arbitrary A, right? I didn't care what A was. Now Z, since I want to prove it's an inverse, I'm going to choose the inverse element of A because, like, if you look at the previous calculation, it's eventually going to boil down to this A0C thing. And if you want to make this an identity, right, the only way is if C is the inverse. And then you'll notice that B0B inverse is E, and so it's invertible. Right, so I'm going to use that fact, right, so it's pretty much the same working as before. You know, that's identity, bam, identity again. Right, and I guess this is kind of like a nitpicky thing, but you need to show it works both ways. Right, you need to show it's invertible with respect to both sides. But then again, the argument's the same, so I kind of said the argument is similar anyway. And hence, every X in HB has an inverse. Right, because I identified it for some arbitrary X. Right, and since we've shown those three things, or two things, we've shown that it's closed and inverse exists, then we can just use the subgroup theorem, where HB is a subgroup of G. Right, this notation, same thing as subspace, or subgroup in this context. Right, morphisms, okay, let's do this quick. This is like the last question. Morphisms is just like, it's like well, you know there's functions, there can be functions between groups. Morphisms are just ones that have this particular property. Order doesn't matter. Right, the order that you combine your elements don't matter. Doesn't matter, you combine it first, then sub in, or you sub in, then combine. Right, so we have this, that. This question. Right. So you have this group, and you want to check that it's isomorphic. It just means that invertible mapping. Right. Right, so similar to vector spaces, you just want to show is there some invertible mapping that exists between G and R. Plus. So the first thing you need to show is that it's actually homomorphic, or there's a homomorphism, because isomorphisms are a subcase of that. So you need to show that. Now, the function, you have to consider, they don't tell you what the function is, but it's not too hard to see what the function would be, because if you look at the form here, it's dependent on t in this one kind of thing. Like, if you look at all this, it's only dependent on a single variable. So that kind of really gives you the hint that the function is going to be the matrix itself. Right, so we'll just work with that for now. If it doesn't work, then we try something else, or we disprove it. Right, so that's what I'm going to do. Right, so I'm going to consider any two STs, right, again, making the argument general as possible. And I'm going to work with, because keep in mind it's got to be FST. You want to prove that this is the same thing as this. Right, so Fs is just the matrix with S instead. T here, just matrix multiply. Right, very straightforward, just multiply here. And eventually you'll see this. And if you observe this part here, this is S plus T. If you look at this, you factorize out half, it becomes S squared plus 2ST plus T squared. And it's just equal to half S plus T squared. Right, very quick observations. In turn, that would say that it's in the above form. right? Just replace this with s plus t. T with s plus t. And hence, you have fs plus t. Right? Because that's how I define my function f. Right? So that means that this is homomorphic. They're homomorphic to one another. Now, the second part is, well, you want to show it's isomorphic, right? So you need to show that there exists some invertible mapping between the two. And luckily for us, if you look at the mapping, so ft was to 1 equals t, 1, 0, 0, t, 1, 0, t squared 2, t, 0, or 1. All of this depends on a single value, and the only way two matrices are the same is if each of the coordinates are the same. So if s is ft, that implies that s equals t. Right, because this part must be the same. Right, because if you look at fs, that will be s. The only way the two matrices are the same is if they're the same, and hence that must be true. Hence, it's a bijection. Well, it's injective, and the fact that it's a bijection kind of just onto just kind of follows through real quickly. The fact that it's real. Right, yeah, should be fine. And hence, the groups are isomorphic. Right. Observing that 1-to-1 isn't too hard, and onto kind of just follows through from the fact. And oh yeah, I guess I should mention why onto follows. Because every g here, you could find some ft here. Right? It's literally kind of by definition. So if you had some sort of function, some sort of element in g here, you can find some t, so just find the 1, 2 index, and just sub it to your function. Right? And then you found an x component that corresponds to it. And kernel is literally just the same thing as vector spaces, except, well, now you use slightly different notation. Right? Identity of the what do you call it? Codomain and projection image. Right, so that's pretty much all for group 3. So thank you guys for coming. Unfortunately, I went over time by quite a bit. I didn't anticipate that. My bad. But thank you guys for coming. And yeah, this recording should be up for a month. I don't know how long it is. Right. And these slides will be up on the website as well. I'm just gonna close that. And yeah, I'm going to stop the stream now. Oh yeah, good luck on your exams actually. I forgot to mention that. Alright. And yeah, make sure you guys come to the Thursday, also Friday. The next 2601 seminar. Right? That's being run by Alex. He's going to do the second half of the course. Right.